Okay, let's get started. So I hope everyone is doing good. It has been a crazy week for me. I was pretty uncomfortable this week, last one. So it's nice to see you again. So, so last lecture I actually recorded first, then upload everything to cloud, then realize all you see was my face there, and so I had to record it again, and the second time I recorded it, it's probably a bit too fast there. We discussed the two topics last week, and the homework is due later this week, so we will not talk about the homework today. We first discussed ASLR, which is address space layout randomization, which is designed to impede um, the exploitations of many vulnerabilities, including buffer overflow and also return-oriented programming, which we will cover in the second half of the class. ASLR has been deployed in most operating systems right now. I mean, most of our um, like a server, desktop, laptop systems, not really those embedded systems. It works by randomizing addresses of a process before it runs, so that an attacker will not be able to know the locations of specific functions, strings, or any other resources. We also discussed SECOM, short for Secure Computing Mode, which allows a process to make a one-way transition into a secure state, uh, where it can only make certain or allowed system calls. So it is basically a firewall for system calls. If you want to know more about ASLR, I would suggest you to read this paper published 4 years ago in NDSS 2016. So NDSS is another top value for security researchers. We have four top values. NDSS is one of them. A lot of important papers came from NDSS. As I mentioned in last class, one of the limitations of the deployed address-based layout randomization for current applications is it is a one-time per process randomization. It happens before or at the process load time. So when you load the process, load the L file, well, I mean, if it's Windows, it's not really L file, it's PE file. When you load a program into memory through the system call, then the kernel will decide where to put each um, segment in the memory. So it's one time. So this is the same as a stack canary, which will not be regenerated when a child process is created. The memory layout of a child process will not be re-randomized when it is forked. So this will be a similar thing as when what we were guessing stack canaries, right? So the address space, the guessing space will be significantly reduced because we can start guessing things one byte by one byte. Here we don't need to guess canaries, but instead we guess the address one byte by one byte. So um, this is a real world problem because many daemon programs, server programs, they will use this fork system call. They will receive some untrusted input. Uh, they will fork to another child process as a worker to handle this. So this paper, um, probably for the first time, uh, I'm not sure, but I think this is probably for the first time. This paper proposed a way to re-randomize the address space of every child after fork at a runtime. Um, so we can you can take like 20 seconds to think about what are the challenges here, right? So if you want to, let's say the program is running, we want to move things around. Want to move the text sections. We want to move the global data sections. We want to move the BSS sections or libraries. Uh, we want to move them around. So what will be the challenges here? Okay, I will give you like 20 seconds to think about it. So the biggest challenge here is when the program is already running, there are so many dynamically created objects or dynamically created data, and there will be a lot of pointers. For example, on the stack, which you have been very familiar with, for each function there will be two pointers. One is save the EBP, which is a pointer to the previous function's stack frame. Then there is also a return address, which is a code pointer, point to a code location. So, so if you run a program with um, many functions, then the stack keeps going, and there will be so many pointers like that. And also there will be other pointers when you reference a string, when you use a malloc to create something on the heap. There will be so many pointers. So which means that if you want to move things around, you have to update, and all those pointers are basically several bytes on the memory, right? It's in the strict address space. Then you have to update all those pointers. So that is the biggest challenge. How do you first identify all those pointers, and also how do you update them? So when we randomize the memory layout before the program runs, things are much simpler because there are not any dynamically create new objects. We only have all the objects we know them at compile time, link time. So link time, we probably need to decide where is your address and updates here and there. But if you're at runtime, things are much more difficult. Um, so this is the paper about ASLR, and I actually believe this area will be very interesting. So I actually am looking for students to work on this with the help of something like FPGA, because I believe with FPGA we can make this even more fine-grained and maybe even faster. And this paper was published in 4 years ago. I think so. If any of you have good experience in FPGA, then you can send me an email to say if we can work on a project like this. Before we talk about today's materials, one announcement. So next week, this is actually the last class before our midterm. Next week, we will have our midterm exam. It will be at the same time as our regular class. The exam will be 2 hours. We will use UBNearns, which is a Blackboard. So I will post questions there. So which means only students who are registered will have access real time. For if you are not really taking this class, I will post this after the class, but not during the class. So you will answer some multiple choice questions, and you will also need to crack some software, kind of like what you did in the homework. So I will give you a link to download the binary. Some of people will use some of the binaries, some people will use other binaries. I will decide that randomly. Then you will post the exploit, post something, a screenshot there. So the exam will be hosted on Blackboard. Actually, I'm still trying to figure out how to use it. To prepare for the exam, I suggest you to go through the slides and also the homework. The exam will take 2 hours, then we will use the rest of the class to go over the exam. So that will mark the first half of the class. Then the second half of class we will talk about very other many interesting things like rob, like attack on the heap, also cache side channel tag, and also format string. Format string is actually a lot of fun. So we will do format string after the week of the meetup. So today,
I
yeah,
had a quick question about the exam.
yes.
So during the exam, are we allowed to reference like our homeworks or like the internet in general, or is it going to be like a closed book test?
Well, this is actually a very challenging part because I have been thinking a lot how to, um, wait, I mean, even if I require this to be a closed book one, I don't think it makes sense. I mean, it's just
Mhm.
basically no way to enforce that, right? So, uh, for example, I mean, there are some special browsers can lock you uh, at one web page or whatever. However, if you switch to another page to try to Google things, then you will send the instructor a message. But the problem is, I mean, you can use your phone, you can use another computer. I mean, there's basically no way for me to really enforce that. So that's why besides those multiple choice questions, so for me, those multiple choice questions, um, I will try to make them that it's not easily Googleable. You know, if you know the answers, if you did all the homework, you should be know the answer. But it's not that easily Googleable. Then for the binaries you are going to hack, those will be new. So you have to do them by yourself. And I will make sure there are multiple versions of them. So if so we have like maybe 14 people in the class. So three of you will be hacking one binaries, the other three will be hacking other binaries. So you will not have the same exploit. But so I will find ways to change the binary a little bit here and there. So that's how I plan to do it. So basically, there is no strong enforcement. It's not possible for me to say, hey, you cannot read a book or even Google. So that means I don't really mind if you Google things. If you need to Google things, as long as you can hack the battery. Yeah.
Okay. I
Basically.
just want to ask because like I guess I wanted to make sure that we can Google the syntax if we forgot something or
Yeah.
the shell code or something like that, I guess.
Well,
Yeah.
I don't think you. Mm,
Or like at least look at the previous homeworks to understand
yes, yes, but also, well, anyway, you cannot cheat. I will design something to make sure that if you cheat, I will be able to identify that. Okay. For
okay.
example, even if you guys are using the same exploit, exactly the same exploit, it probably will generate different things on different computer. Okay. But if you give two people give me the same thing, then I can easily notice that you guys are cheating. Okay. So don't cheat. You are not supposed to talk with each other. Um, that's the rules. So I will announce the rule next week, but I just give you a heads up. Yeah. Okay. So today, oh, by the way, tell you a funny story. So a friend of mine, Adam Dupay, who offered a similar class at Arizona State. So his class was a little bit different. He spent like a whole summer, like 3 4 months. The first time he taught that class, spent the whole summer, 3 4 months setting up the cloud environment. So the students they actually uh, hack into use that cloud environment. So everyone has an account and hack level by level. It's kind of like a maze or vortex, the wargates. So basically, that's what we're going to do for the final CTF. But I needed time to set things up like that. So during the semester, they have like 14 or 15 challenges. And each week, they have to do a one or two. Then one of the students, he actually, yeah, it's a male. I'm not trying to hide he is male or female. So he uh, send a phishing email to all the students in the class, which is a big class back in Arizona State. There are probably 30 to 50 people. So he sent a phishing email to many people in the class, pretending he was the instructor and he want to check if they know what is the correct exploit. Then several students find out this is suspicious. So that guy registered account like blah, 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 adam.dupay@gmail.com and send out the message. So which means by that email address, you don't really know who that guy is, right? So some people actually send him the exploit, and some people find out this is suspicious and report to Adam. Then Adam quickly reported this to the dean's office. However, they don't know who that guy is, so they need to find a clever way to do that. So in half a day, they decide that they were designing a exploit to a certain project, to a certain level, then ask one of the students to send that exploit to the student. And when that student runs that exploit, it will expose who he is, right? So any idea how to do that? It's kind of like a share code, right? So the share code will not only give you a share in this case. The share code probably will get who is a user, right? Get a user ID, then write that user ID to some file or somewhere. Then it exposes who uses share code. So then they call the student eventually, and eventually that student didn't get his master's degree. So, well, this is just a story, don't cheat. Especially during this uncertain time, there are so many ways you can cheat, but don't do that. I will try to find ways to detect those behaviors, and if I find out, it will be very serious. Okay, so today we will be talking about developing share code, and we will use several examples to show you how to write share code. So today we're changing things a little bit. Today I want each of you to actually write share code. We're going to program assembly here, but what we are going to program is not very long. It's just 10 lines of assembly instructions, at most 20 lines in this case. Nothing super complicated. If you are interested in share coding, there are actually many books. So one of them is very famous. It's the Share Coder's Handbook. However, this book is not only about share coding. It's actually about system security in general. It covers buffer overflow, all of those things, and it has many real-world examples of share coding. So before we start, I will show you. Have you downloaded the code from the website?
Yes.
Okay. So if you downloaded the code from the website, you will notice that today I have several codes there in that tester folder. So it's just everything is in that tester folder, and we have tester 32-bit version, 64-bit version, and we have three different testers. One is called 0, that's a level 0. Then we have non-zero, that's a level 1, and also ASCII, which is level 3. And I also give you two templates there, share-code 32-bit templates and 64-bit template. You can see the main difference is this is basically where you can get started writing share code. And let's go through the tester.c first. So tester.c is basically a C file for you to test your own share code without actually just trying to hack the victim program, just to test your own share code. So you can see this program uses a system called a map to create a memory page, and that memory page is 4 KB. So 1000 hex is actually 4 KB. So that's big enough for our shellcode. Our shellcode usually is like very small. What are you doing, Jeremy? Do you want to say hi to everyone? No. Then you have to go away. No, I'm teaching. I'm teaching. I have to go. Okay, you're tired. Okay. Sorry for that. Everybody's tired. Yeah. So, so let's create a memory page, which is 4 KB. Then we set this memory page as readable, writable, and also executable. We don't really care where we put this memory page. That's why the first argument is 0. So in the mmap system call, you can give it an address, and it will use that address if it's possible. So if you give a 0, means you don't really care what is the return address of page. So if we get this memory page, then we will just read from 0. This 0 is STD in. So standard in, we read there for whatever you input. Then we put them into the page. Then we just run whatever is at this page. So you can imagine, so this is very simple for us to test our shellcode. For example, we have anything. Oh yeah, we have our samples, right? So we have a shellcode 32-bit version template. Let's say this is not really a valid shellcode. It's not going to do. Yeah, it's it has several instructions, but it's not going to give you a shell. So what we can do is we can. Oh, and also, oh yeah, this should work. We can compile this use long std static runs to 22-bit version. Then the output, let's put shellcode 32. Then shellcode 32 template. Let's see if it works. Oh, it works. Okay, so there's no syntax errors. Now we have this shellcode here. Then we need to do an object copy. Let me see if I have an object copy there. History object copy. Okay, let me just copy one of this. So what we did just now, it will generate an L file, but the L. So we will basically get a L file there. You can say the shellcode. What do we generate? Shellcode 32. Okay. So shellcode 32 is an L file. So you can just run it, but that's not a very good shellcode. That's why we're second and fourth. But because it's L file, it's a big file. It has a lot of meta information. It's a big file like this. If we only want the code part, the text part, we can use object copy to get that part. So we can do object copy dump section. We're going to dump the text section, and we dump it to share code 32 raw. Then dump from this share code. This is the input file, which is an L file, and this is the output. It's the raw file. And after we dump this, we can see we have a new raw file, which is very small, only 25 bytes. Right? And we can take a look at this. It's only 25 bytes. Okay. So to test this shellcode, what we need to do is we just need to cat this shellcode file to our tester. Of course, we need to have 2 cats there. Then we redirect this into the std in standard in of the tester. Go to your 32-bit. But this is not, so this is how we test it. So yeah, this, you don't have this file. Okay, set it to 0, okay. Yeah, so let's see if it works. See, now we run, when we run anything, it says segment fault. So basically we are running the shellcode, uh, but it's not working there. Um, so this is our program to test our shellcode, and I have a different version of this. Why I have different versions? Because by modifying this program, you can try to replicate the victim environment, the actual hacking environment you have there. So here it's like we're not doing any sanity check of the shellcode. Whatever you gave me, I can run it, right? But in real world programs, they may doing all kinds of sanitary checks. There are many different restrictions that do not allow you to do certain things. And that's what we're going to learn later. Okay. So before we start writing our shellcode, let me remind you how to invoke system calls on x86 and also 64-bit version machines. In the 86 x86 machine, the system call number is set in EAX. The registers we're going to use include EAX, EBX, ECX, DX, so A, B, C, D, plus ESI and EDI. So then we were going to run that int hex 80. So note that we're using ATAT syntax. So if this is an immediate value, you have to use a dollar sign. Okay. Otherwise, you compile it, you will compile into a memory location. You will treat 80. If without this dollar sign, you will treat 80 as a memory address, not an immediate number. If you care about the return value will be stored in EAX. Sometimes we don't really care about that. The example here we have is we want to call this system call exe CVE. Then if you want to know what system calls are there, you can go to this website. It lists the system calls for different architectures. You notice that the same system call may have different numbers on different architecture. Even for 64-bit and 32-bit, they have different number. And if you want to know what kind of argument you can give to a system call, you can simply do a man exe cve. Then it will bring you to the manual of the system call. So note that here we have the section 2. Section 2 means this is the system call section. If you don't trust me, you can do a man, which you get the manual of man. Right from there, you can say, so those are the sections in that Linux manual. The second section is for system calls. The third section is for library calls. So if you do man exe cve, then it will give you, this is a prototype. So basically, so the first argument is the path name of the program you're going to run, then the command line arguments you want to give it, and also the environment variables you want to give it. But here you cannot really tell the system call number. That's why you have to go to the website to find out the system call number. So this part will be in EBX. This pointer will stored in ECX, and this one will be in EDX, and the system call number will go to EAX. Of course, if you program in C, you don't really directly call system calls like this. Okay? So if you program in C, probably do something like this. You probably use the one of those 6 functions to execute a program. You never use the exe cve to execute the program. You use the one of those. Okay. So all of those functions. So you notice that the section number here is 3. So those 6 functions are not system calls. They are just a ramp of the system call we just discussed. And eventually, all those functions were called the system call, but they provide a slightly different interface for developers, just to make developers' life a little bit easier. For example, so L here means list. V here means vector. So you can say if we are using L list, so this function actually takes arbitrary number of arguments. So this is like a printf function, or this is called a variable length arguments. You can. So you basically, if you want to put different arguments there, then you just put them as argument one by one for this function. Then this function has to put them together into a vector or array to call that system call. For example, LP, which means what's the difference between this one? I'm not sure. For example, E means there will be environment variable. So first you put the arguments here, then you put the environment variable here. So that's what you call when you do C program. But we're not doing C programming today. We're doing assembly, and we are directly calling system calls, so we are not going to use them. Then one more thing is how do you create a string? For example, this one we are going to call the system call, and the first argument will be the address of this string. So we need to somehow put this string in the address space, or if there is already the strings in the address space, you need to find out where it is, like what we did in return to libc. But for this one, let's say we don't know if there is one. We just need to put this string into the address space and get the address. So how we can do it? So we can simply use a stack. So we can first push 0 there. We push a 0 there, which is the end of the string. So this 0 actually could be 4 bytes. Then we push this constant, which is basically those letters. Then we push those letters again, so they form bin sh. After we push this, who points to this string? ESP points to string. Then the second, the EBP actually points to, EBP is the second argument, should be set the address of this. That's why we just move ESP to EBP, then we can have the string in the address space, and also at the same time, we can have the address of that. Okay, so next, we are going to write this shellcode. Even though you have been using this shellcode for the buffer overflow class, the shellcode we're writing right now will be a little bit different. It will be a little bit simpler actually. Let's try to write the 32-bit version first. I need a volunteer to do this and share the screen. So and everyone else, you can work on your own computer. So who wants to be the volunteer? If there's no volunteer, I will just call outside. How about you lead the first one?
Okay.
Yeah. So I will give you the control of the screen. Then you can share your screen. Then everyone else, get your environment ready, and let's see. So what you can do first is to make a copy of that 32-bit version shellcode. Yes, you can make it a 32. Yeah, that's good. Yep, you can use whatever editor you're familiar with. So what is our goal here?
We want to push the string to the stack and call the system call.
Yes. So yeah, as simple as that. So let's see. How do you plan to do it?
I don't remember those strings.
Yeah, you can copy from the slides. Do you have the slides download?
I cannot download the slides.
I will give you guys the string in the chat box. Just give me 1 minute. I'm giving you guys 3 instructions, and those 3 instructions will put the string on the stack. Okay. So it's 3 pushes. I think you can just copy that. Yeah. Yeah. Note that when we have immediate numbers, we have to use a $sign. So if you don't use a $sign, it will be treated as a memory address. Okay, so now what do we have? We have the string on the stack. What's the next register we need to set?
Recipe or not?
Where do we store the system call number?
Year X.
Yes, year X. So you need to set year X somewhere. Yeah, the number is hex B. So $sign, then 0x. Yeah. So if you push it, then what you need to pop it, right? So
we have the string, we have the year.
This is interesting here, right? So when you start writing assembly code, you realize there are just so many ways you can achieve the same goal. If you want to move some value, immediate value, to a register, you can simply use the move instruction. Or what she's doing here actually will work. She's trying to push that immediate number to the stack. But what to do next? You need to pop it. Right? But another thing you need to consider here is, yeah, there is actually a move instruction where it makes sense easier, but what you're doing still work. And sometimes you have to use that, maybe. I think it's actually the wrong order. That's a wrong order. The first operand is actually the second operand is the destination. So you need to move $0x OB 0B to EAX. Yep. So that's how it works. So now, are we ready? Do we need the string at the bottom? We don't really need that. We can delete that, right? Yeah. Okay, so can someone find any problems in this shellcode? By the way, the template I gave you only defines that there is a underscore start function. There is no, which means there is no main function. And when we compare this, when we link this, we didn't link with the standard C library. So this program, even if it's a big L file, it only has one function, which is the underscore start. Okay. Why don't you just try this? We don't know if it works. We just try. We just compare this.
Let's try this.
Yep.
Registers are supposed to have the $sign data $sign.
Yeah. Let her try.
Okay, see some arrows here.
Yes.
UX, EBX.
Yeah, I don't know who said that. Yeah, the registers is the percentage sign, not the dollar sign.
Oh, yeah. Yes. Yeah, you're right. Thank you.
Okay, cool. Then everything else looks good.
So what's the?
Can do GCC. Oh, yeah, that's the one. Yeah, can use that one.
Okay. Sorry, I shouldn't run here. This is another environment. Okay. Junk. Oh shit.
9.5. Yeah. Then we'll have an L file. You can simply run the L file to see if it works.
Yeah,
Yep,
it works.
it works. Oh, yep, so it works. Then you can try to dump, dump the extra share code.
Dump section xt. Okay.
You don't have the
Oh, it's
program.
0.
Oh, yeah. Yep, you can do an ls to see if it works. Nope, it's not working.
It's not working. Yeah.
Okay.
Question.
So,
could we go back to the shellcode again?
Okay.
I'm not sure if I think I missed a couple. So the first 3 pushes are the bin sh string, correct?
yes.
And what is so E0B is a call to the exec v, right?
Yes, that's number 11 in decimal for the system call. Yeah.
And what is ESP, EBX, and AT?
So that one. So where does ESP points to at this point? It points to that string, right? Because you only have 3 pushes there. After that reach 3 pushes, you have the string. So basically,
bottom of the stack, I guess.
Yes, you are moving the address of that string to EBX.
Yeah.
But is it correct that we're moving to EBX and not? So what is EBX in this case?
For 32-bit version, it should be EBX. So EBX is the first argument.
EBX.
Right?
EBX.
EBX is the first argument.
Yeah.
EAX is the system call number.
Oh, okay.
Yeah. So here, one possible problem is, can you try to make ECX and EDX, which is the second and third argument 0 as well? Probably that triggers a problem. Yeah, I'm not sure, but let's see.
0 ECX.
Yeah, and move 0 to
0.
Yeah. So anyone else, if your shellcode is like she's, do you have the same problem?
Yeah, I got the same core
down. Okay. Cool. Then she, you are missing something there.
Oh. Where?
After 0.
Oh. Okay. Fine. Yeah. Let's try this again. Compiler. Oh,
Okay.
now it works.
So looks like the reason is the previous version, she didn't set the second and third argument to 0. And those arguments at some point was used, right?
Yeah.
Then there is probably a bad dereference. That's why you get this error.
Mm.
Okay, so this is our first version for 32-bit. Oh, she, can you hold on?
Okay.
Hold on.
Oh, wait a minute.
Do you mind showing me the shellcode one more time, just so I can make sure I have it right?
Sure.
Okay, thank you.
Okay.
Okay.
I guess I can copy it to the chat.
No, don't do that. I don't want to. I want everyone to type it. Okay.
Oh, okay.
Yes, I mean, even if you type it, just typing it, even if you know how it works by typing it, you learn a lot. So, okay. So here, why don't you show us? Let's do a XXD on the raw file of the shellcode. XXD. Just do a XXD. Yeah, on the shellcode. Yeah. Yeah. So what do you guys notice here? Is there any special characters here?
2 edges.
That's not a problem. You see a lot of zeros here, right?
Yeah.
A lot of zeros. So, which means if you are using something like a string copy, this shellcode will not work because the string copy will stop in the middle of the shellcode when copying, right?
Yes.
So let's say, could you please cant this shellcode to a different version of tester, the non-zero one? To the non-zero one, okay.
Last one.
This is 0, non-zero, low zero, sorry.
This one.
Yeah. No, you're still doing the 0 one.
Oh, I see.
Yeah. Then you try to run this, it will not work, right? Because you didn't fully copy the shellcode. At some point, you reach 0, and the CPU will just treat 0, 0 as the machine code and try to run from there. Then you get a second fault. Okay. Okay. Thank you, Shi. Then we need another guy to do the 64-bit version. Hold on. Let me share my screen first. Okay. So for the 64-bit version, things are actually a little bit easier. The system call number is still in RAX, not EAX anymore, RAX. Then the arguments are also changed. This is more like the arguments we see in the function calls in 64-bit. So the first argument is in RID, second RSI, RDX, then R10, R8. Instead of using int 80, there is a special instruction on 64 version, which is a syscall. And we're going to use that one. And we can directly, the return value will also be stored in RX. And also, how do we create string here? There is a convenient way for us. We don't have to push things there. Instead, we can use this piece of code. We first define a string at the bottom. So bottom means higher address, actually. Then we have a label. So this is a bin sh. The label, what you call it doesn't really matter. Then in the code, you can directly use use load effective address instruction and use RIP as the base register. This is not possible in the 32-bit version. In the 32-bit version, you cannot use EIP directly, but in 64-bit version, you can use RIP directly. So then you can use this one, then RIP, then you can directly get the address into RDR. Then you set up the second and third argument, then you do system call. So anyone want to lead this one?
Sure,
Anyone?
I can.
Uh,
If that's not a problem.
Sure.
Yeah.
Let me give you the control here. Go ahead. So you can copy the 64-bit version of the shellcode.
Okay, so
So the first thing you need to do is figure out what is a system call number, right? I think 59 is correct. Yeah.
I'm just removing those unnecessary things. Okay,
Mm-hmm.
59 was the correct call.
I think so. Yeah.
Okay, I forgot how to check. Is there?
There is I give you guys on the slides. There is actually you actually have the link with you, but that's a picture, I guess. So let me.
I just took a screenshot of your while you were presenting.
Real quick, I've got 59 decimal for EXE CVE.
Okay.
Okay.
So that's correct. Yeah.
You said 59 decimal. Okay, yeah.
Decimal.
Yeah,
Yeah, that's decimal
Okay.
there.
Okay.
So are we moving to RAX or EAX?
RAX, yeah.
Yes, we're moving to RAX. Then
Is it also RSI? Yeah. Wait, no. So the first argument is the bin sh.
Yes, it should be in RDI. I think I had a typo there. I said RID. Yeah, RID is not really the same. Yeah. So the screenshot of the slides, there's a typo. Should be RDI.
This.
Yeah. So the first argument on the slide says RID. There's no such thing as RID. Should be RDI.
Okay, and the first argument is a string, and I don't think I have that slide where you said how to get the string.
Okay, let me copy that too.
Hey, Beck, I think you already have it loaded in the template.
This right here?
That's so then you, oh shoot, I just.
Yep, I just sent you in the chat box. So that is basically, you have the string there, but you need to get the address of it, right? So how do you get the address of that?
Yeah.
Yep, right here.
Mm-hmm. So note that the base register we're using here is RIP. So we're actually only getting the relative distance between RIP and the string. Yeah.
But RIP. So here's my question. So doesn't RIP change like on every
compiler or something, or every run?
No.
Yeah.
Yeah, every instruction, right?
Yes, but this is a RIP when this instruction runs.
Oh, okay. So bin sh is accounted for like when this instruction runs. Okay.
Yes. So it's like the compiler needs to decide what is the value of bin sh. You don't care, right?
Okay.
Yeah, you just treat that as a label. Yeah.
And I don't have any other arguments, so I guess I will move the zeros to the rest of the arguments.
Exactly.
And I think it only has 2 arguments, aside from the one that you were giving it. Yeah.
Didn't we have to, in a previous example, didn't we have to set 0 other registers?
We only set 2 more. Here the same. We only need to set 2 more.
Okay, so
second and third.
Okay.
Hey,
and yep, go ahead.
That move 0 RDI. I don't think you need that.
Oh yeah. No, I don't need it. Good catch. Wait, so the first argument RDI, and then RSI is 02.
Yes.
Okay. So I don't need even R10. Okay. Okay. And AT stands for syscall, right?
That's for 32-bit. Right now it's 64-bit. So you need to. Oh yeah. You're right.
Okay.
Change that to syscall. Yeah. Change that int 80 to syscall.
Okay, and I guess, okay.
And try to compare this. There is an M32 there. You need to remove that.
Yep.
Okay. Good.
I guess the rest of the flags are correct, right?
Yep. Actually, now you have an air file. You can do an object dump. I want to show you the label there. Object dump. OBJ dump. Sorry, OBJ dump.
And then we pass it the shellcode 64.
Yep. Now you see that we actually only have one function here, right? Which is the underscore start. But this disassembler is not that smart. It doesn't know our function stops at the syscall. It shows everything after that is still code. That's why even though the bin sh is not really a function, it's just a string.
Yeah.
But the disassembler is trying to disassemble that as a function. That's why it believes there are two functions. Another thing you notice that in your share code, in your assembly code, you are using bin sh rip, but check the second line of the start function. The start function.
Yeah.
So it's not that anymore. The compiler will calculate the distance between them and change that to a constant.
So so RIP at this stage is for this.
Yeah.
Yes, I need to do this.
Yep.
Oh, I guess is this 10?
Wrong order.
Yeah.
Wrong order.
Negative
Wrong
number.
order. Yeah.
Whatever. We say this works. Okay.
Yeah. Did you do? Yeah, you can directly run it first.
Shellcode 64.
Yeah, it works. And to debug this, you can also use strace to see what's going on. Yeah.
Okay.
And there's another trick I want to teach you guys is, everyone ever think about how debugger works? How do you set a breakpoint?
Yes.
How does, well, without a hardware debugger, we're just talking about software debugger. So why would that program stop at some point? Why would the program stop at the breakpoint? How does it work?
Function pointer matches where you told it to break. Is that right?
Yeah, go ahead. Who was talking first?
Yeah, Phil was talking first.
Yeah,
but
Phil.
I was about to say, I think operating system offers some ability to essentially do all this stuff, but stop the program. And I remember you cannot actually do things with that functionality in elevated programs because it will drop your privileges. That's why you cannot really get in GDB you cannot get elevated root shell even if you debug the Yeah,
that's a little bit different thing. I'm talking just about why your program stop. For example, when your program is running on the CPU, how can it stop? It must be some kind of an interrupt happens, right? And the interrupt could happen because there's a hardware, or the interrupt is some kind of a software interrupt, like the int we're using. So to implement a breakpoint, so all the debuggers is actually just add a replace the original code to an int here. So we're going to say this in a minute. No, this one, what are you doing? Oh, this one doesn't work. Hey, this one doesn't work. Do you know why? Or anyone has an idea why this one doesn't work?
I have a better
because
one.
of the bin/string, like we're dumping the text only.
What?
My 32 doesn't work too. I'm not sure why, but 64 doesn't work too. Yeah.
Well, so what are you counting here? You are counting the L file.
Oh, okay.
Right.
Yeah, we didn't text dump it yet.
Oops.
Yes, you're counting the L file. So it will just use whatever out of the L file to as a shortcut. And at the beginning of that, it was just the magic number. Yeah. So you need to do the, no, this one doesn't work. That word.
Wait.
You didn't generate the raw file.
I did.
You did?
I think, yeah, I did generate the 64.
That's an L file.
Oh, okay.
Right? That's not the machine code. You need to use the object copy, obj copy. Yeah.
Well, what's the? I think you had a long instruction to actually do that. I don't remember the entire instruction.
I can read it.
Okay.
So the object copy, flag dump section. Yeah, dump hyphen section. You got it. It's after that dot text equals, and then you're gonna call whatever your raw file name is gonna be. Great, space, and then the target, whatever your ELF is now.
Mm-hmm.
And I think you're ready.
Yeah.
That's what my other one didn't work. I missed that step. Okay.
Now it works. Okay. Then another thing I want to show you guys is how to debug this. Let's say if you want to debug your shellcode and run it with a tester, how do you plan to do it? You use a GDB tester, right?
Yep.
Yeah, you can do GDB tester.
Oops, my computer is a bit.
So we're using tester 0. Yeah. Tester 064. Okay. So where do you want to set a breakpoint?
In which function? It's
the main function is eventually going to call that. Yeah. So you can set a breakpoint at the last line, I think. The indirect jump, the indirect call. That's it.
This. Wait.
Yeah, that's it.
I think I need to. Oh yeah, this one. No.
Yeah, just the one is fine. You don't need the 3 of those.
Yeah. Was it shellcode raw like this?
Shellcode 64 raw, I think.
64, yeah. Oh, I think I need to do like this first, and then when I actually run it.
Yeah, that's the actual address. Yeah.
You need to get rid of that.
Yeah. How do you delete a breakpoint?
Do info break. I think it's break 1. And then delete. Just type in delete 1. Should get rid of that. You need info breakpoints out though. There you go. I think you're ready.
Okay.
Okay, you're there. Then you can do maybe SI. Oh, you're here. Yeah.
Okay.
So you can do SI to get into your shellcode.
SI?
Yeah.
Yes, okay.
Mm-hmm. So now you are in your shellcode. If you disassemble that, well, you need to use exam, I think, because it's not really a function. X means exam. Yeah. Like 10i, yeah, that's fine. Then the address. So this look a little bit weird. That doesn't look like a shellcode.
I think it might be because maybe colas. Maybe we need to do the next instruction.
Oh, so
It
we're
wants
not
to
there
jump
yet.
somewhere.
Yeah.
Yeah.
Probably we're not there yet. Okay.
Okay. There's a jump.
No, it's just the next line. Yeah.
Oh, okay.
So can you get out? So that's why I want to teach you a trick here.
Okay.
Well, we can make this work, but there is a trick I want to teach you.
Do you want me to exit the GDB?
Exactly.
Okay.
Go to the shellcode source code, the assembly code. I want you to edit that, to change that actually. So you can manually set a breakpoint here by yourself. So the breakpoint is actually one special instruction. So what debugger usually do is, no matter you use GDB or a debugger with GUI, you set a breakpoint. What the debugger does is to replace that instruction where you set a breakpoint as a new instruction, a special instruction. And that special instruction where it's an interrupt. It will go to the kernel, it will set a breakpoint. And that instruction is actually int3. So why don't you add a int3 before the move? Yeah, just int $3. Yeah, that's it. So when your program runs, it will treat this as a breakpoint. When you do GDB, it will treat this as a breakpoint. So it will stop at the beginning of your shellcode.
Oh, okay. So GDB doesn't like append, it replaces it, and then when we continue, it replaces that interrupt 3 back with a normal?
Exactly. Okay. That's how your debuggers work, software debuggers. Yeah. Hardware debuggers may be a little bit different, so they use different features.
So when we continue with the execution, does it move EIP back 4 to re-execute the same step without interrupt
Yes,
instruction? Okay.
Exactly. Not an EIP. It will actually replace the instruction back to the memory space. Because the debugger does is to change that instruction. Well, compare this. I will show you.
Okay. Okay.
Yeah. And this one is only 1 byte. That's why it can be anywhere. No matter the original instruction at this place is 1 byte or multiple byte, it can be changed to this one because this instruction is only 1 byte. Yeah, you can compare this, then do an object dump. You can say that. Then do an object dump of this.
Yes, I need the GTB now. Okay.
Object dump. Do an object dump.
I already did.
And this object copy. I mean object dump.
Oops.
To say that this assembly. Should say CC, that 1 byte means this is a breakpoint, but it's actually an interrupt. So when that happens, your program will switch into kernel mode, and the kernel will replace the original original code back if there is any. In this case, we don't have any. But now you can just go to GDB and you don't need to set any breakpoint because you already have a breakpoint. Yeah, you can. But there is a segment for it. Can you disassemble here? Looks like. Can you just do a
Yeah.
maybe do a just use exam to say where are we at? The exam, the
Oh yeah, my bad. Yeah, this.
Hey, Beck, you can just run it off of a EIP or
yeah, so
RIP if that's easier.
this doesn't look like our shellcode.
I'm actually seeing mine work.
Yeah.
Okay, so all right, let me repeat the steps one more time.
So what did we miss here?
I think ABEX source and mine are identical, so I don't think that's an issue.
Okay, so this is the source. Here I will compile it.
I do not see any problem here.
Here I dump the raw section. Next I GDB test 64.0. I run.
I think, hey, ABEC, it might make the difference that you're using too many standard ends here. I think
just use one. Yeah.
Oh, okay.
At least I hope that's what was wrong.
Is that what you used?
Yeah, it worked for me when I did this.
Oh yeah.
Yeah. So now the signal is a signal trend, not the segment fault. So you, I think somehow we were 1 byte off because of that.
I think he was using shellcode 64 before, and now he put raw, so it was different things.
Oh,
oh maybe. Okay.
Maybe.
Yeah, maybe. Yeah, that's maybe a reason. Okay. So see, so you didn't set a breakpoint at GDB, right? But GDB stops at it here.
Yep.
That's because that's a system call. Okay. Cool. So that is.
How does it?
Go ahead.
So when GDB replaces an instruction with the
int3,
it replaces like where does it keep the copy of the replaced instruction?
Well, GDB itself can remember that. It's basically just 1 byte to remember.
Okay.
Right.
So it's okay.
Yeah.
In what we did, we're not really replacing, we're actually prepending the instructions, so it's not replacement.
Exactly.
Okay.
Exactly. Yeah. This is also related to there are a lot of debug registers. So depends on how you use them. They can the software debuggers like GDB, they will use those debuggers to do it. Yeah. Those registers to do it. Okay, cool. Then we are going to move to the second one. Going to stop ABEX screen sharing. Okay, so you notice that the tester we used just now, we're just copy whatever you have here and run it, no matter it has any special characters or not. So the next one, we will make this a little bit harder. We will, instead of run anything, we will just read whatever you have into a buffer. Then we will use a string copy to copy what you have in the buffer to the actual shellcode place to execute. So which means string copy will not copy zeros, right? If there are zeros, it will not be copied. That's why she just showed us the 32-bit version of the shellcode we developed. If we send it to the tester no zero, it will not work. So now I need another volunteer to develop a new version of the 32-bit shellcode, and this time we don't want to have any zero there. Who wants to do this? Sereni catch, can you do it?
Yeah.
Okay, so I'm going to give you the control.
Quick question.
Sure.
I also think I missed this part. What's the difference between the zero and non-zero?
The string copy.
Oh, okay. So in non-zero, we just use this. Okay, I get it.
Non-zero, we use string copy, which means your shellcode cannot have zero.
That makes sense. Okay.
Yeah. Yeah. String case, you can take control, share your screen on. Cool. Do you have the 32-bit version ready? 32-bit version of the shellcode ready? The one she developed?
Yes.
Okay. You can. Okay. You can make a copy of this. You can make a copy of this. Yeah. Change to no zero. Copy. Don't move. Yeah. To a low zero version. Yeah. Yeah, okay, so how do we know where do we have the zeros? If we want to remove the zeros, we first need to know where we have the zeros, right? How do we find out that? Any idea here? How do we find the byte zeros there? We do an object dump. Get out of this, get out of Vim, then we do an object dump of that old version. The old version of the 32-bit, yeah, shellcode. No, the alpha, 32-bit.
Oh, okay.
So yeah, remove 32. Looks like you don't have 32 there. Yeah, that's it. Okay. So this was the shellcode that works for the tester. And however, she showed that this one doesn't work for tester no zero. Then let's say how many zeros are there? There are, the first instruction, there is a zero. After 6A, there's a zero, which means when she copied that, we only copy 1 byte, right? We only copy 6A, then we stop. Then there's 3 zeros at the fourth line, four zeros, 6 9, and another 4 zeros. Okay. Our job, yeah. Go ahead.
What is the purpose of the first push 0 0?
The end of the string.
Oh, okay. Okay.
Yeah, that's okay. Now, our goal is to remove all the zeros from the machine code, from the binary. You understand what I'm saying?
I have a question.
Yeah.
Can we specify the size of what we're moving?
Yeah, we actually can. Yeah. We can use something like push B, push L, push W to do that. Yeah.
Is that going to help us here and get rid of some of these like trailing zeros?
For example, the first one doesn't, right? because even if you just, for the first one, actually the compiler is smart enough to say that we are only pushing 1 byte. We're not pushing 4 bytes.
Right.
The other ones, the problem is, even if you can do that, for example, you change to, let's say you change to move B0 to CX instead of ECX.
Right.
Or change to CL instead of CH, because CX is still 2 bytes. So we're changing to CL. What will happen is that there will still be 1 byte of 0. Not 4 bytes, but still 1 byte, right? Because that value 0 will still be there. So it doesn't solve the problem. Yeah. So that's why we need to find other ways to do this. There are just so many ways to do this, but Srenikis, do you have any idea? How can we do this?
Can you purposefully offset the address? I don't know.
Can we XOR the register with itself?
Okay. Okay. Then what do we do? For example, the first thing we want to do is still put a 0 on the stack, so it can be the end of that string, right? But no matter what instruction we use, we cannot put a 0 there. Okay. So can you go to the code? Let's do this. So who said that we can XOR the register there?
Me, Charan.
Okay. So Charan, so what we can do is, can you delete that push 0? Instead, we can do a XOR. Let's say whatever register we want to use. Let's say
Yes.
EBX maybe. Yeah. It doesn't really matter. Yeah. So EBX. So you have to use $sign here, not the no sorry, percentage sign, not $sign. Yeah. Okay. Again, you need the EBX. So you want to use EBX to with EBX. Okay. So what will happen after we execute this? The EBX will have 0, right?
Yep.
But we still do not have that 0 on stack. So what do we do? How do we put that on stack?
Then push it.
Push it.
What? Push it? Yeah. Then why don't you just push EBX? Okay. Then get out, compare this, and let's say if we get rid of that 0. What's the problem here? Do I have any special character there? $sign.
What was the error?
The error was. Oh, you didn't compare this as a 32-bit version. You were comparing. You need the M32 there when you compare this. Yeah. The error is the size. No. You cannot put it there.
Before dash O.
Yeah, you have to put it before that. Yeah. Yeah. Okay. I think it's there's no.
Yeah, there. Yep.
Yes. So the problem is you compare your 64-bit versions. They are looking for another instruction like push L maybe. Otherwise, the original push they are expecting to push something 64-bit. That's the reason. Yeah. So now you say,
yeah.
The previously we have like what 6A00 something like that. Yeah, 6A00. Yeah. Now we replace it with 3 bytes, and there is no 0. Okay. Now let's do the next one. How do we? The next 0 will be move EBX EAX.
So XOR them again, like we did before.
Yeah.
Oh no, not that.
Wait, but EX had the zeros, right?
Yeah. So how do we do this?
So where does the 0 come out here? Because of the 000B, or?
Yes.
So
because we are moving things to EAX. EAX is 4 bytes. That's why there are 3 zeros. The most significant 3 bytes of EAX.
what if we XOR EAX before that, and then we move to AX?
Yes, that's a good point. But we're moving to AX or AL. Probably AL is enough. Yeah, go ahead.
Yeah, I don't remember the register. Whatever the smaller registers.
Yeah, then we
The
need
last
to
4 bytes.
yeah move to AL. Change the second line to AL instead of EAX to AL. Yeah. Then maybe we need to change the move to move B, add a B after that. I'm not sure if that's necessary. The compiler, no. Just the move to move, add a B after the move, MOVB. Change the instructions to. I'm not sure this is necessary. I think the compiler will identify that, but you can try. Yeah.
Let's try.
Mm-hmm. Yeah, we'll get rid of that. Okay, looks good.
Just those last 2.
The last 2 will be easy, right? We just need 0 there, then we can just do XOR. Right?
Oh yeah.
So we can do XOR, we can add a number, we can set a big number to it, then subtract number there, or add a small number there, then add a number there, right? So there are just so many, or you can push something to the stack and pop it. There are just so many ways we can avoid dollar percentage sign. Is it EPX? It's a lot of register, right?
Oh, was EBX?
Oh, it's EPX? Okay. I thought it's EPX. It should be EPX actually.
Oh, EDX?
We had ECX, EDX, like almost flexibly before.
Oh.
Yeah, so this is 32-bit version, yeah. Yeah. Try this again. Okay, do we have zeros?
No zeros.
No zeros. Okay, we're good to go. Let's try. See if it works. Yeah, we can use both tester. The 0 tester, it should also work. Then we can test the non-zero tester. Yeah. Okay, it works. Then let's try the non-zero tester, low zero tester, sorry. It's called tester no zero. Yeah, 32. Yeah. It also works. So that's because we get rid of the zeros. Okay. So that's the 32-bit version. Who wants to do? Thank you very much. Sereni Kiss. Yeah. So who wants to do the 64-bit version? Charles, did you raise your hand there?
No, I was debugging my 32-bit version.
Okay.
And I was trying to. Mine still has one bug, and I'm not sure why.
Do you want to show us? Do you want to show us your code? Yeah.
Sure, I can do that.
Yeah, I can't compile either.
Oh, really?
Uh,
Did you compile with M33?
Yeah, not quite. No, I'm getting an error on that first Zor. I'm not exactly sure. I might have missed a character in the source code, but I thought I was tracking well.
Okay. So
You want to
Charles,
maybe put a screenshot? You can upload the screenshot. We could take a look.
yeah, Charles, you can share your screen first.
I'll look.
Let's take a look at Charles' code. Maybe.
Should I put it on Slack? Should I put the screenshot on Slack?
Trini, that would help me if you could.
So
I tried it this way, which was a little different.
Okay.
Because ECX and EDX are the two arguments.
yeah. So we have using EAX there, then push EAX, then push those strings, moves it to EBX, ECX, EDX, then move this to EAX. Okay. Oh.
Wait,
problem.
it's yeah.
Yeah, go ahead.
Isn't well, my thought process was you again move 0B before EAX. You're moving B and not 0B, and you're moving it to EAX. Doesn't that introduce already a 0, 0?
Yeah, that should be 0, 0. If you compile this, you do an object dump. There should be a 0 in your code.
Oh, you're saying where you do the 0x B?
Yes, because of that one. Instead of doing that, you should move to instead of moving to EAX, you should move to no, not that one, not the register. Instead of EAX,
AL.
AL.
Oh, EAL.
Yes.
Or AL.
No, AL.
AL. Yeah.
Which means you have to move B instead of.
Yes.
Gotcha.
Yes. If you compare the previous one, you will get 0, 0. Yeah.
That's that one, and then just all right, thank you.
See, that's a problem. Thank you, ABAC, for that. Okay, so we need another volunteer to do the 64-bit version.
Did Phil resolve his issue?
What?
I'm looking through Shini's source right now. It still looks identical, but I'm missing something small, I'm sure.
Okay, Phil, do you want to share your screen?
I can. I'm using a different machine than my Zoom for my
I see.
environment.
Okay.
I got cold feet after other people were having VM problems and mine locked up, so I migrated over to my Linux system, but it doesn't have a webcam, so I didn't log into Zoom from it.
Okay.
I can switch, but it's going to take me a little bit of time.
Maybe put on Slack your problem so we could later take a look at it.
Yeah, yeah, I'll just fire that up real quick.
Okay. Let's wait for Phil a little bit. Then, who is Dark Angel here? There's a Dark Angel here.
No, that's my device name. Sorry.
Okay, it's okay. So, so who are you?
Kamlesh.
Okay, so do you want to lead the 64-bit version?
Yeah, sure.
Okay. Maybe wait a little bit. Let's wait to say Phil is going to share something there.
So I put that up in the Slack.
Let's see.
The compiler error pointed out EBX, but that's not what it seems like is the real issue.
Did you use the M32 there when you compare it?
Yeah. I'll run it again real quick to see if I can get I'll go ahead and paste the error.
I think you are moving 0x0b to AL. I think that's it.
That looks correct to me.
I see. I think you're not putting the system call in EAX. Your EAX is.
Srinivas has that.
Oh no, never mind. No, my bad.
Yeah,
My bad.
yeah, it's,
That makes
EAX
sense.
is good. EAX is good. EBX looks good too. ECX is 0, EDX 0. Everything looks good here.
Yeah,
What does a compile give you?
Yeah, what?
So that error points at line 5. I put the
Oh.
error just below. And that's push EBX.
Oh, it's possible that you cannot push EBX. Really?
Did that not work for Srini? It looks like Srini was able to.
Oh yeah, how do you push EBX? Like, because push affects EBX, you might want to use a different register. No.
No. EBX is not affected. No,
I'm
push
getting
EBX.
I'm getting a similar error, but I'm actually getting it with register ECX.
Okay.
Which is further down in the code.
Maybe my M32 is in the wrong place. I don't think that would matter, but.
Can you show us that?
This is how I compiled.
Yeah. Yeah, show us. Also, whoever was speaking there, you can also post on the stack to say, especially your command to compile that. Maybe that's the problem.
That's the full.
Immediate register operand EBX.
And again, that picks out the push.
Try EAX just with maybe different register.
You can try EAX, but I think you can't push EBX. You can push any register.
Yeah, it should be. We're gonna zero whatever we use.
Yeah. So Jackie also got a similar problem there.
It's a different line.
But it's a different line. Yeah. So Jackie, is your line 11 also a push?
Does the GCC compiler care how you pass in the arguments, as in which order you pass in the arguments?
I don't think it matters. Yeah. No, he was talking about the command line arguments. I don't think that. Yeah, I don't think it matters there.
Okay.
Yeah.
Because I had static and then M32 and then -L, but I know some are, I guess that shouldn't matter.
Yeah, I don't think it matters. Yeah. So what could be the problem here? So everyone else get it running?
Okay, so I figured out what I was doing wrong. At one point, I had identified the file name as a .c instead of a .s, so all of my updates were going into a file that I wasn't compiling.
Okay.
So eventually, when I started pointing to the correct file, I was able to compile. So I think I'm probably caught up now.
Okay. So maybe Jackie has the same issue there?
Yeah, it might be. I'm gonna look into it right now.
Okay. Then Gersimran is also asking, so Gersimran, what's the problem you have there? We cannot really see because.
Yeah, I need to shellcode.
Yeah, I think the code is fine because I ran the program and it ran correctly. But when I'm trying to run it with the tester program, it's giving a segmentation fault.
Yeah, but first of all, you need to verify that there is no 0 in your shellcode, right? So
okay.
By showing the screenshot, we cannot confirm that, and also you're not showing the code there.
Okay. Should I share my screen?
Yeah, you can share your screen.
Okay.
Yeah, you can share your screen now.
Okay. Can you see my screen?
Yes.
Okay. So
Can you show us the share code first?
okay.
I think you need
The second to last XOR, I see ECX XOR with EDX.
Oh, okay.
Oh, yeah. Yeah, that's probably the problem.
Oh, it worked.
Yep, it works.
Yeah, yeah. Thank you.
Okay, yeah. Okay, now we are, Jackie, did you solve the problem?
No, not yet, but usually I have to watch every lecture again. So I'm going to go through the lecture again and find out, because up until this point, I've gotten everything. And this is my first issue.
Okay, then we are moving to the next one. Whoever Doc Angel is, take over.
Yeah, 1 second.
So now you can share your screen. So now we are moving to the 64-bit. Oh. So do we have the previous 64-bit with 0? Do you have that version? It's better we modify that version. Try that share code 64S. Probably that's what you have there. Yeah, that's it. So this one, let's do object dump to say how many zeros we have. Where are they? So then we know what do we need to change. I'm not sure if this. Oh yeah, that's the version. Okay, seems like there are so many zeros. The first one we have 0. The second one we have 0. The first 9 we have 0. The second 9 we have 0. The third 9 and the fourth 9 seems easy. We already know how to do it. We just use XOR. Okay. How about the first 9? First 9, any idea? How do we? Okay, this may not be hard. We just XOR RAX, then move 3B to AL, right? So that could be one way to do it, I think. Then we move 59. Yeah, you have that. Yeah. To AL. Yeah. That should solve the problem. And also the last two you can change to XOR. Solve those problems.
What exactly is the AL register used for?
What?
What exactly is the AL register used for?
Oh, so the RAX is the 64-bit version of the register. It has many parts. For example, that register is 64 bits, and the lower 32 bits of that is called EAX. Then the lower 16 bits of the register is called AX. And in that lower 16 bits, we have AL, the lower part, and AH, the higher part. Each of them is 8 bits. So this is compatible with the very, very old 86 CPU, which is a 8-bit CPU, right? So that time they probably call the register AL. Then they changed to the 16-bit CPUs, and they call it AX. Does that make sense?
Yeah.
So your code, you can still run super old code because that. Okay. Okay. Now we removed most of the zeros. Now we just need to remove that load effective address. Okay. How do we do that? Looks like here, line, the third line. Looks like here, looks like this instruction is 7 bytes, and the 3 bytes, the first 3 bytes are just opcode, so that part you can not change and you don't need to change. Then the last 4 bytes are the relative address, which is 4 bytes. So how can you remove those zeros? Any ideas here? Anything you guys want to try, just to say it, right?
I mean, we could try to X or out the RDI register, but I have a feeling there's going to be a repercussion.
How do you plan to do it? Can you repeat that again?
It's an odd number of bytes that I'm trying to work with in my head, so I don't have a good strategy.
Okay. Well, one of the things we can do is instead of using EIP-based addressing, we go back to our stack approach. We push, right? Like what we did in our 32-bit version. Then we should be able to get rid of that zeros because we're not using, because the problem here is that we are using the distance between that instruction and the string being sh, and the distance between them is very small. That's why it's just 8 in hex. It's very small. That's why the other 3 bytes will be 0. The other way, that's one of the ways to do it. Another way is maybe we can try, instead of putting the string at the end of this shellcode, how about we put the string at the beginning of the shellcode? Oh no, that doesn't work because we're going to jump to the beginning. Okay, that doesn't work. Okay, looks like the easier way is using the stack approach.
Can we maybe like use the negative of that number somehow?
That's what I'm saying. That's what I'm saying. Yeah, right. To use the negative number, we need to put the string being sh in the front of the shellcode. But when we copy it, it will execute there. Oh, it still will work. We put a jumping instruction at the beginning. That makes sense. We can put a jump at the very top of our shellcode. It's a jump. Then after the jump, we have the string. After the string, we have this the current shellcode. So that the bin sh will have a lower address as the RIP, so it will give us a lot of F, right? But when we execute that, we will skip that string part. Yeah, that should work. Does that make sense? Okay, anyone get what I'm saying here?
I think yes. So you're gonna put that LEA bin sh at the very end.
Yeah.
Oh no, not.
Not at the very end. The very end should be a jump or something. But you need to
Yes.
make
Yeah.
sure that but you need to make sure that jump doesn't introduce any zero there. It may introduce a zero because you're jumping to a relative address, so it may add a zero there.
Wait. If we put jump after the zero zeros, jump would not be included.
Like which zero zero?
So what introduces the 0, right, is the wait. What was it?
I mean the jump instruction itself may introduce several zeros there.
Okay.
Because the jump is going to jump to a later address, right? A higher address, and the distance between them is short. If the jump is relative addressing, it may have the same problem we're having now, basically, just for jump. Yeah. So instead, I mean, how about to save time? How about we just use a stack for now? So you can copy. You can use same as the 32-bit version. We put the string onto the stack.
Should we take advantage of the push that we can use right away since we already zeroed out the RAX register?
Yeah.
Okay.
Good point. So you have a very good point here, because sometimes when we're developing shellcode, another constraint is the size.
Did that make sense to the presenter? So I'll wait until you're able to get the string set, and then I have one piece of advice that'll help us save some space and time.
Can like someone guide me through this and just
Oops. Are you still online there?
Yeah.
Okay. So what you can do is you remove that load effective address line, because we don't need that anymore. Now we pushed the string there. We just need a 0 byte at the end of the string. So end of it. So you need to push 0 first. So, but you don't want to push 0. And what a fail set is, we can utilize the first XOR. So you cannot push 0. If you push 0, you will bring a 0 there, right? So you need to push RAX, but right now RAX is not 0 anymore. So you want to move those two pushes before the line of move 59. Yeah, that one move to the so that line you can move
Oh crap. Okay, nice. So the idea is that since we have a purely empty RAX register already, yeah, there you go. Next instruction, we can just push that on the stack.
Yeah.
I did try that, and that ended up being a segfault too, but maybe it's a little slow.
Charlie, I can't hear you. I'm sorry.
I was saying I tried that as well, and I still got a seg fault on mine.
Okay.
I'll try to fast forward and see what happens.
So let's see. Okay, looks. Did we? Hold on. We didn't move this to. We didn't move this to the first. Which register should we use? Our. This is 64 bit. The first argument goes to RDI. We didn't move the string to RDI, right? Did we? No.
No.
No, yeah, we need to move that.
Oh.
Yeah. You missed a line of move RSP to RDI. Move.
Yes, that's right. We got to move the stack pointer.
RSP to RDI. Yeah, that should work. Nope. Somehow we jumped to somewhere. By the way, you can remove the string at the end because we're not using them anymore. The bin sh. Yeah, that one we can remove it. But what is the problem? So someone is saying, let's see. Okay, we can debug this. You can set up int c at the beginning of this thing, then we debug it. Int3, sorry, not c. Int $, nope. White space int white space $, yeah, that's it. Now we compare it again, then we debug. Okay, so I'm using M64, that should be okay. That should be the default one. Then do a obj. Oh yeah, we can. Let's debug this one directly instead of one. Yeah, we can debug this. No, the L file, so not .s. Yeah, you should have the L file. Okay, then just run. Okay, now we are here. Just do SI. Let's say if everything works right, then RAX is 0, then we push it. Okay, go ahead. You can just enter. Then, oops. Is 3B correct? Oh, 3B is correct. Then we push the string. Go ahead. Push again. Okay, here let's do a x slash s. Let's do s because we want to check the string is correct. Then do RIP. No, you don't need the address. You just need $sign RSP. Sorry.
RSP, yeah.
Yeah, RSP. Let's see. The string is not correct. We don't have the full string here.
Maybe we don't do RSP, or you need X
Oh, I know what the problem is. I know what the problem is. Think what the problem is. When you push, okay.
We're pushing 32-bit.
Exactly.
Strings. Yeah.
So we're pushing some zeros there, right? So instead of, how about you do a X 2 strings or 6 to maybe 10 strings, maybe S 10, yes, then do that. You can see, yeah, we push a lot of zeros there, see? That's a problem. Because when we push, we're pushing 8 bytes, but we are only giving it 4 bytes. So we push a lot of zeros there. So we can just combine those two into one push. And it's exactly 8 bytes. So put those two numbers together. Which one should be lower? Yeah, just copy the second one at the end of the first one. That should do it, I think. Is that order correct? I think it's correct. Yeah. Copy this to the end of the first one.
Yes, I think that should be, yeah.
Right.
Yeah, so just paste.
Yeah. You just remove the second line. Yeah, that should do it. Did I miscopy the 1 byte or something? I'll try. Should we push or push? Looks correct to me.
I think we have extra, no?
Oh, I think you cannot direct it to a push because of the 64-bit version. You cannot direct it to a push like this because the instruction is too long. You need to move this to a register, then do a push. That's just a limitation on the, for example, let's move this value. Instead of push, we do move. Change that push to move. You still need the $sign, yeah. Dollar sign. Not the percentage, yeah. Then let's move this to a register like which one we're not using. It's RBX. Yeah. Then we just push RBX. Yeah, that's just an architecture limitation. You cannot push a big number like this. Yeah. Then try it again. Now it works. Yeah.
I think you need to use move queue and push queue. At least I saw it on some place.
Oh, really? Okay. But that part should be automatic, right? I mean, the compiler should know that is.
Maybe I'm not sure. I just looked at the online and they use push queue and move queue, but yeah, maybe that works too. It doesn't.
No, it's still not working.
Oh yeah, you need to remove the I3, I think, and 3.
Oh yeah, you have a breakpoint, but okay.
So when I debug that move, it flipped the move instruction to move absolute value.
Yeah. Yeah, it works now.
Oh, nice.
Yeah. So, can you try what IBEX says there? Let's try push Q. I don't think it works, but let's try.
Oh yeah, I take it back. Mine worked fine.
Okay.
So move Q and push Q, and so the ones in the middle. So no.
Yeah, we don't need to. We are going to push directly, right? So you don't need to that push. Push Qs and remove that. Yeah.
Oh yeah.
Yeah.
No. That's not what I said. I said
Okay.
like literally everything what was there before, except instead of push you use push Q, and instead of move you use move Q.
Oh, that part doesn't matter because the
Okay.
compiler will automatically decide that.
Okay, then it's fine. No, then.
Yeah. So this one should not work. I don't think there is an instruction like this, but yeah.
Okay.
So this one will be the same as push. Push Q, push will be the same. Yeah. This should not work. Okay. So how about everyone else? You guys get it working?
Yes.
Yeah, mine works.
Yeah.
Okay.
I'm assuming push Q just means push quad word.
Yes.
Yeah.
Exactly. And there's a compiler where, or technically this is not compiler, this is an assembler. Assembler where based on the size of the register, they will decide that. So you don't need to tell them specifically you are using push Q here. Yeah.
Dr. Joe, a quick question.
Sure.
In the debugger, I was successful, but I'd also used that int3 break. So when I tried to run it just now on no zero, I got a trace breakpoint trap core dump. And so does that mean I need to pull the int3 out before it's going to work as an exploit?
Exactly.
Yes.
Yeah,
Okay.
you need to remove that part. Yeah.
Cool.
Okay, so we are going to move to the next one. So I'm going to share my screen, and now we are moving to the next one. Okay. So the homework for you guys this week is to do the tester ASCII. Okay. So I'm showing you the code here. This one is even more strict. You can have 0 there, but you can only have ASCII. So ASCII is from 0 to 127, right? Besides that, it's not ASCII. So let me show you. My browser. So ASCII table. So ASCII table is from 0 to 127. So you can only use bytes, machine code fall into there. So you have to do a lot of testing here and there. Do the 32-bit version first, then think about the 64-bit version. 64-bit version actually is very tricky because the syscall itself doesn't fall. The syscall, so this is syscall. If we do, let's see, I have a compiled one, non-zero, down the which browser? Shellcode 64 non-zero. So Cisco 04 is OF05, so that is fall into ASCII, so that will not be a problem. Okay, so that should be okay. So this is the source code of tester ASCII here. You will only copy ASCII once. Okay, so that's will be your homework. Then let's keep discussing other things. So
is the homework we due next week, or is it going to be like 2 weeks after?
It will be next week. Okay, let me think about it. I can give you guys several extra days. Yeah, I will give you guys several extra days because next week anyway we're not going to discuss the homework. We're going to talk about the exam. We have the exam. So yeah. Okay. Keep moving forward. So you can see developing shellcode is actually a lot of fun and a lot of dirty work there. A lot of tricks you can use. I was searching something. If you search GitHub, there are a lot of tools to automatically generate shellcode with the equivalent shellcode and ASCII shellcode or alphanumeric shellcode. You can consider alphanumeric shellcode is you have an even smaller space to work on. So basically, you can only choose things from here 48 to 57, then those bytes. Okay, you have an even smaller space to work on. But someone, actually already 10 years ago, someone brings this to another extreme. Is in CCS, one of another of our top conferences, CCS, 2009 has already 10 years, 11 years. That's when I started my PhD actually. So and I was working on share code detection that time. I used machine learning. I used data mining, try to detect the share code. Then this paper came out. So basically, kill all my share code ideas. So this paper, it's called English share code. So you can read this paper. What they did is they developed a tool to generate share code that reads like readable English. Okay, it's not good English, but it's readable. For example, this paragraph, okay, look at this paragraph. There is a major center of economic activity such as Star Trek, which doesn't make sense that much, but still it's readable English. You may get confused, but it's still English. And this thing is not only just English or text. This is actually share code. So if you disassemble this, you will get this share code, and at the end of it, it's always a jump. So for example, this is actually the vanity part. So this is only the part to make it sounds more like English. Then it jump to here. This part is a vanity code. Then jump to here. Then jump here. So they add a lot of here. Then jump here. But this is vanity share code. So which means if your, let's say your instance messenger have some kind of vulnerability, buffer overflow, and someone is chatting with you, and you thought that guy's chatting with you, but maybe he's sending you share code. There's no way you can tell. I mean, this just reads like English. So this is actually this is amazing. So that's the English share code part. So share code right now, especially because of this paper came out. So imagine before this paper came out, there are a lot of papers using all kinds of heuristics and also machine learning, data mining things to detect if this piece of data is share code. For example, if it's share code, we disassemble it. Usually you have several int, right? It has several push, and use those patterns. We can, if you just disassemble some garbage, obviously it will look different. So use those heuristics to detect if what we received from the internet is share code. So this can be part of your intrusion detection system. And instead of, so you know, the old antivirus systems using some signatures, and also your intrusion detection system using some signatures. And these signatures can be changed. You may, for example, that share code, you transform it in another way, it will look totally different, and those signature doesn't exist anymore. However, even though the signature doesn't exist, the pattern may still be there. That's all the ideas. Then this paper came out, basically here's that there is no pattern in share code. The share code can look like anything it wants to look like. Okay, so there is no pattern. That's basically how it works, and that will conclude our discussion in share code, and I will send you guys the homework later. So I do want to summarize a little bit what we have been doing so far this semester, the first half. So we worked on, the first thing we worked on is actually reverse engineering. Every class, every homework, you worked on reverse engineering. You tried to understand what this disassembly code means, look like. That's the first thing we worked on. And the second thing we worked on is stack-based buffer overflow. And in the first half, I actually emphasized a lot that you should get the accurate offset, accurate address for those buffer overflow. So your exploit were all handwritten, handcrafted, and you need to get the accurate address. But in real world, that may not be the case. First of all, sometimes it's impossible for you to get the accurate address because you do not have access to the binary code. You cannot disassemble that. For example, you are hacking a remote server and you don't have that remote server's code. What you can do is just keep trying. And that's when the tools like Pwn tools we used last week or 2 weeks ago can become very handy because those are programmable that enable you to write programs to hack. And you can just trying things there. Then we talked about return to libc attack. We talked about several defenses approaches to stop stack-based buffer overflow and return to libc, including stack canary. And we saw that how we can bypass stack canary, especially when it's a forked program. Similar approach can be used to bypass address-based nail randomization for forked program. Then today we talked about Shellcode. So I would say based on your homework and everything, I think most people are doing great in this class, and based on my interaction with you in the class, most people are doing great. Next week, let's put that into test. Then the second half of the semester, we will do something even more interesting than what we have done so far. Okay. So any questions there? Any questions? No? Everyone's good? Okay. So if everyone is good, then I will see you guys next week. I will let you know when I post the homework and everything. And good luck on the exam. Okay.
Thank you.
Okay.
The only thing I was going to ask mention is the slides on the website for this week aren't up. It has a 404 error.
Oh, really? Okay, I will fix that. Yeah.
And like, I guess, is this lecture included in the exam, or is until like up until
included? Oh. Yeah. Okay. Any other questions?
No.
Okay. Good.
I had a question like, will our homeworks will be corrected before the exam so that we can get the feedback, or is it possible? Or
for this week's homework, no. But for other, the previous week's homework, I will grade it soon, so you can get the feedback.
Okay.
Yeah. Okay. Cool. See you guys next week.